I would like to present my thesis with the title Accelerated Methods for Computing Acoustic Sound Fields in Dynamic Virtual Environments with Moving Sources. So first, I would like to talk a little bit about what is virtual acoustics, why do we need it, and what are the challenges. Next, I would like to talk about two machine learning methods for predicting the sound field for handling dynamic scenes. Then the second part will be a bit shorter. Here I will talk about an attempt to make an accelerated acoustic solver by using domain decomposition. And lastly, I would like to do an outlook and conclude. So, virtual acoustics is a widely used term referring to the simulation of realistic acoustic environments not using a computer. And the goal is to recreate the auditory cues to give the listener the impression of being in a specific physical space. So this could, for example, be useful in computer games.
Time to get the hell out of here.
Hey, are we not going to talk about what happened back there? With the nest? I mean, what the hell was that?
It looked like they were transforming.
So recently, many of the big tech companies are getting their take on the next generation digital worlds. And so with these new digital worlds, for example, this could be a situation where this would be an education situation where people would interact with some virtual elements and maybe go back in history and learn about some things in life. Also recently, we have seen the introduction of spatial computing. And spatial computing is not a new term, but it's actually referring back to 2003. And that was defined as human interaction with a machine in which the machine retains and manipulates reference to real objects and spaces. So the industry trend is clearly going toward more immersive experiences blending the virtual and the real worlds. And this has application not only in entertainment, but also for productivity tools and for people to meet virtually. And of course, the visuals is important, but also the acoustics is very important to make right. And therefore, we need to develop new methods for capturing the acoustics. So, what does it mean to capturing the acoustics? So, the way that we capture acoustics is that we inject some energy into the room. It could be a pistol shot, and then you would record the reflected sound in some receiver position. And the characteristic of the room, of course, it depends on the geometry, but also the materials on the wall, how it absorbs and so on. And it consists of first a direct sound, so you see a source up here and a receiver. Then we have some early reflections, that is when the wave is bouncing back a few times, and then the late vibration. And this is what we call, so these things here is what consists of an input response. So of course, so now we have the characteristic of the room, but now we have some sound source, and we want to reproduce this sound source in this room where the input response is captured. So how do we do that? So this would be our sound source, and this would be our input response. So a way we do this is kind of a mechanism where we blend two signals together. And when we do that, we get the audio signal out as it was played in this room. And something to note here is that the sound signal you want to reproduce should be dry, so it shouldn't already include the duration and so on. So how could an acoustic rendering pipeline look like? So we have a modeling part. So we need the room geometry, we need the boundary material, and we need the sound source, where the sound source is located, and then how the directivity of the sound source would be. Now we want to propagate the sound right, so we need to capture the early and late reflections, and we need to capture the underlying physics. So here we see some of the effects. So diffraction is what happens here at a corner, so you can see the wave bends around the corner, and the scattering is what happens over here at the right side here, while wave comes in and then gets reflected in different angles back. Another physical effect is interference. So when two waves meet, the result is basically just a sum of the two sound waves. Then there's a rendering part. So we are human beings, we have 2 ears. If we want to reproduce the acoustics with, for example, headphones, we need to do, for example, binaural rendering. We need to do some source interpolation and source moves. But we can also choose to render for, let's say, the surround sound systems. So this last part here has not been considered in this project at all, so I've only been focusing on the two first parts here. So before starting building new methods, it's a good idea to look at what are the requirements for interactive applications. So from a usability point of view, we want to automatically calculate the acoustics from predefined scene geometries and boundary materials. So we want to handle dynamic scenes, so we can have 100 moving sources and receivers, and eventually the geometry could change at runtime. At the same time, storage should be limited and computational effort should be small. And from a perception point of view, we need realistic acoustics for the intended purpose. So there are mainly two approaches for calculating the acoustics. So there is numerical methods for solving the wave equation. So the wave equation implicitly takes into account all these effects that I just talked about. Then we have another type of methods called geometrical acoustics, and this is a simplified method where the waves are approximated as rays. And the benefit of this method is that it's very efficient, but the downside is that it's less accurate, especially for the lower sound field. So we have made some assumptions for this project here. So we want to accurately model acoustics and also the low frequency sound fields. So the geometrical acoustics are not so well suited in that case. So what does it mean, low frequency sound fields? So I want to play some samples for you. The first one is the full bandwidth that sounds something like this. And the low pass clearly a difference, but we still notice that a lot of information is still kept even at 1000 hertz. So when we're using numerical methods for solving the wave equation, there are some challenges because the way that the numerical method works is that you typically discretize the domain into a grid, and then you calculate the sound field from a given source position in all the points of interest. Now, every time the source moves, we need to recalculate the simulation, and that can quickly get difficult. So here's an example showing this. So this is the room of 9 times 3 times 7 meters. So, and here we see some calculation times done by a very efficient in-house GPU-based GGBIM solver. And we see when we go up in frequency, the computation time grows very rapidly. So because of this, with these numbers, we cannot do real-time simulations. So what's typically being done is that we pre-calculate the impulse responses and we save them. But this gives us some other challenges, and that is depending on our resolution or on our source and receiver positions, we need to calculate between 300,000 and 5 million impulse responses, requiring storage between 600 and 9 gigabytes. So these are some challenges. So our approach is different. So we want to build a model that somehow can give us the impulse response in real time. So this model should capture all the physics, all the physical effects that I already talked about, and then we have the modeling part, room geometry, boundary materials, and sound source, and we could use this as an input to our model, and then the model should output the wave field, something like this. Now we could change the root geometry, the boundary material, and the source position. It would give us the sample for a new geometry. So this would be like, if we could do this real time, this would be fantastic. For this project, we have been a little less, more realistic. So what we have done here is to move the boundary material and the root geometry into the model. So that means we create or we learn a model for specific boundary materials and a specific root geometry, but we keep the sound source as an input. That means that we should be able to change the sound source and get an output resource very quickly. And it's also very useful to move the receiver position out, because typically we don't need to get the full sound field for the whole domain. We just need the sound field for the receiver position, right? So we need the input response that I talked about before. So by moving the receiver position out, we can get the input response for a source and receiver pair. And now we can use this to do this blending with our sound source and get the acoustic out. Get the sound. So we have made another assumption. So to accommodate the computation demand, we allow for offline calculation. So this means that this model that I showed before, we allow to pre-calculate this model. So before going into what I have developed, I would like to give a brief overview of the state of the art. So I already talked about two main methods, numerical methods and geometrical acoustics. The geometrical acoustics are very efficient, but they are less accurate, especially for the low frequency. So this is not really useful for us for our goals here. There exist many numerical methods. I've just listed a few here. The finite spectral element methods, the finite difference time domain method, and the Fourier methods. And the benefits of these methods are that they are accurate, flexible, and reliable. The downside is that they are expensive, and especially for dynamic scenes. So when the source moves, we need to recalculate every time. Yeah. So actually, all these methods here, I have used them in the method that I developed in paper D. So there exists another family of methods that are quite new. So these are the data-driven and scientific machine learning methods. And here I've also listed a few of these: physics-informed neural network, neural operators, implicit neural representation, reduced order modeling. And the benefit of these is that they allow for very efficient evaluation, and they can also handle parameterized partial differential equations very well. So that means that we can change the sound source, and we can still predict the input response. The downside is that they can be very expensive to train, and it's not always, and it's also can be difficult to ensure convergence. So the first method here is what I have used for paper A. The second one, the neural operators, is used in paper B and C. Now, reduced order modeling is some of my colleagues who have used this method, and it's basically a method to reduce dimensionality. And in this work, it was used for parameterizing the boundaries, where you could change the types of materials on the walls. And then there's a relatively new family of methods here, implicit neural representations. And these methods are inspired by computer graphics. And in that way, for example, for predicting input responses, it's not only taking the source and receiver position, but it also takes some visuals. So it could be some angles of the scene, and this helps the network predict the input responses. So we take a different approach than this. So our methods are, our approach are built on combining the knowledge from scientific computing with machine learning. So that if we have a physical system, we try to include some knowledge of the physical system into our model. And this is what I would like to present here in the first method, the physics-informed neural networks. So traditionally with deep learning, it's a black box. So you have some kind of network that you train from some input and some output, and you hope that this model can predict whatever you want to model. With physics-born neural network, we include knowledge about the physical system that we are solving into the system, and by doing this, we hope to get more reliable results. So I'll briefly show some example here of how PIN works. So let's say we have a mass spring system like this. We have some observed data from this system here. So what we could do is to train a black box deep learning model by minimizing the loss from the observed data and updating the weights by using back propagation. And then we would get something like this. So it fits very well to the points, but outside it doesn't work. It doesn't fit very well to the platform. So for pins, so this problem here, this is actually described by this equation here, this physics. So what we can do, we can include this knowledge into our loss function. So we still have the data loss, but then we add another loss here, minimizing the residual of the physics. So, and actually calculating these terms here are quite easy because we can use automatic differentiation already available in those frameworks, so that we can take the derivative of the output with respect to x, we take the second derivative and so on, and then we minimize this loss. So this is basically what it is. And now we see that we can actually fit outside the data range. So the observed data points. So what we want to model here is we want to learn a surrogate model that had taking three inputs, x, which is the receiver position, x0, the source position, and t is the time. And we want to model this surrogate model through a physics-born neural network. So by doing this, we can feed in a pair of source-receiver pairs, and then we can get the impulse response over time for any time distance t. So our problem setup looks like this. So this is the wave equation. So P is the pressure, C is the speed of sound. And we also need some initial conditions because we need to inject energy, and this corresponds to our source. And we model this by using a Gaussian pulse. And the reason why we do this is that we can change the width of the Gaussian pulse, and by doing that, we can choose the frequency we want to span. We also have to model the boundary conditions, so depending on the materials on the wall, this has to be modeled as well. So our research question is, can pins parameterize the source position in predicting wave propagation for impedance boundary without using data? So this is our wave equation, and this is expressing the wave propagation. But we need to handle, as I said, also the boundary condition. So if we have frequency-independent boundary condition, this is the propagation. And we have to solve this system at the boundaries. So we use this equation inside the domain, and when we reach the boundary, we have to solve this equation. And the side here is the normalized impedance. So this is depending on the type of material we want to model. So for frequency-dependent boundary, it's slightly more complicated. So when we have frequency-dependent boundary in the time domain, we need to solve this equation at the boundary. And V here is the normal velocity. So we need to find a way to calculate this velocity. And this can be done by this expression here, where y, a, b, and c is to be is determined by the type of boundary material we want to model. And phi and psi here are given by another system of coupled ordinary differential equation by this. So this means for frequency-independent boundary condition, it's fairly simple. We need this and also the initial condition And for free to dependent bounds, we need to solve this one by also solving this couple system and then insert it into this formulation here and solve this equation as well. And this is what we want to solve without using data, but only using the automatic differentiation in physics formula methods. This is how it looks. So we have two networks. This one is predicting the pressure, and the other one here is predicting the so-called accumulators. These are the coupled ODEs, so the solution of these. And the loss functions that we want to minimize is given by this. So we have the loss of the underlying here, the wave equation. We have the boundary condition, and then we also have these coupled differential equations that we need to minimize. And all these terms here can be calculated by doing automatic differentiation of these outputs with respect to either x or t. So I'd like to show the results. We have a 2 meter domain, and max frequency is 1000 Hertz. Simulation time, is 0.012 seconds. And the material that it's a porous material of 0.10 meters and a flow resistivity of 8,000. So the first row here is showing the wave field. So it's 2 meters minus 1 to 1. The columns here are the source position. So you see that we have different source position given by this. And the dotted line here is the where we call the input function. Think about like a microphone capturing the sound. And we now see that the wave travels in both directions. It gets absorbed when it hits the boundaries. And over time here we see this is the pressure point at the, so this is the result of the microphone, the recorder, the input response. And down here is the error at the time. And we see that, so the dotted line and the solid line here are the reference and the prediction, and you see that they fit very well. Actually, it's around 2% relative errors here. So now we want to solve the same problem, you can say, but this time we are using another type of network, the deep neural overlay network, DeepNet. So the research question is, can DeepNet parameterize the source position in predicting the wave propagation for complex and realistic 3D scenes? So before we had this, so this was our physics neural network. Now we want to do the same, but with this DeepNet. And the main difference between, let's say, the physics neural network and DeepNet is that the DeepNet is approximating operators instead of functions. Typically in machine learning and deep neural networks, we approximate functions, but with DeepNet we approximate operators. So now the main difference now is that instead of giving the source position, now we give it a source function, so a function to our model. And the way that the network is set up, I will go more detail in a moment, is to take the inner product between the so-called bracelet and the trunnion. So we still, so by giving the input, so the source function at some position, receive position and time t, we can now again predict the input response. So as I said, DeepNet is approximating operators. So we want to learn an operator, and let's call that operator G. So now G takes a function u and outputs G of u, which is also a function. Now, for any psi in the domain of G, G of u of psi is a real number. So it's important to note here that the operator G takes in a function and outputs a function. And now we want to evaluate this operator at some specific locations. So here are some examples of operators. It can be differentiation, it can be Fourier transformation, it can also be partial differential equation. And this is what we are concerned about here, because the wave equation is a partial differential equation, and we want to learn the operators of this field. This is how a DeepNet looks like. We have two networks, a branchlet and a trunklet. The input to the branchlet is a function. In our case, it's our initial condition, our source function. and the trunket takes in the positions, so the location where we want to evaluate our overrating. And yeah, this is how, and then we take the inner product between the output of the two branches, giving us the solution of giving us the operator applied to the input function and the locations. And this is how it looks in a numerical way. And if we look at this, we can actually see that it's actually a series expansion in terms of the basis functions modeled by the trunket, and then multiplied by the corresponding coefficients predicted by the branch net. So this is maybe a more intuitive way to see this. So this operator network is built on some theory. So there exists an approximation theorem for functions, but there exists also an approximation theorem for operators, and it actually goes back to 1995, and it basically says that we can find a neural network that can approximate the exact operator with arbitrary precision bound by this epsilon. But this theorem doesn't say anything about what type of network and what optimizer to use. So this is just a theoretical foundation that it is possible to get an arbitrary precision. So what are the inputs? I already mentioned a couple of times. The input to the branch net are the source positions, so different source position. The input to the trunket is where we want to evaluate the system. It doesn't need to be the grid, it can be in a continuous grid. And then we input the time t, and then we should get something like this. And then it doesn't need to be evaluated in all the point. We can choose a single receiver location and just get the response over time. So a few things that I learned by setting up this network is that using a modified multi-layer perception architecture increase the capacity of the network by a lot. So by having, so up here we see like a standard LNP. So the modified LNP basically lifts up the input to the network by some encoders, and these encoders are multiplied in a specific ways in between all of these layers, and this helps the network propagate the information better until the last layer will actually do the data modifier. So this drastically helps. Another aspect that is known is it's not only an issue for deep nets or physical network, it's general for deep learning. This the spatial bias, and it basically tells us that neural network starts learning the lower frequencies first, and like a smooth version of the result and then it starts trying to learn the higher frequencies. But it can actually there can be some problems with the network actually learning the higher frequencies. So there exist some methods to circumvent this. So this shows the loss over time by using a hyperbolic tangle function with the standard LNP, and you see that basically it doesn't learn anything. Now, if we do Fourier expansions, this is a way to help the network. It's a transformation of the input to the network in a way that looks like the solution, or resembles the solution in some way that helps the network now learn the higher frequency content better. And you see that now it's actually much better. But if we use the sign function, we get even better results. And if you use the sign with the modified LNP with positional encodings, we get pretty good results. And this is what we use for results. I'd like to show some results. Again, we simulate up to 1000 Hz, simulation time of 50 milliseconds. For frequency-independent boundaries, we use a normalized impedance of around 18. For frequency-dependent boundaries, we have a material thickness of 0.03 meters and a flow resistance of 10,000. And the first result I want to show is the result for this acoustic domain. These are the dimensions of the outer dimensions of the L-shaped room, and red area here is where the source is allowed to move. Over here we see the reference, we see the prediction, so this is the full wave field, this is just a cut through the domain. And over here we see the input response for a source receiver, source position and receiver position. So the source is located around here, and now we see how the wave propagates in the domain. So up here the reference is the dotted line, and the prediction is the solid, and we see that the two input responses fit very well together. And this is actually a quite tricky case, because we have the effects that I talked about earlier, so the diffraction effects around the corner. And in this case, the source is located here and the receiver over here, so there's no line of sight between the two positions. This shows that this method actually gets pretty good accuracy in not so easy cases. Another case we did is the furnace room. Again, the red area here is where the sources are allowed to move. And the source position is located here, receiver is located here. And we again see how the wavefield travels and it gets reflected at the boundaries. Here, again, we see good results, but not as good as before. We see some parts here that are not as accurate as before. You can also see that from the root mean square error. Before it was 0.05, and instead now it's 0.09. But still a pretty good match. The last case I would like to show is the dome. So this is the most complicated one we have here. So we have this sphere, and we have these different here. And the red area here is where the source is allowed to move in. So in this case, we did an experiment. So we did the simulation in the full domain, but we also did domain decomposition to see if we could, by doing this, get better results, more accurate results. And actually we could. So the domain decomposition works in the way where, so the source can still move the full domain, but the neural network is only trained in this area. So we cannot predict outside, we just get some random results. But you can say overfits to this area here, so to speak. And we see very good results by applying this domain decomposition method. We see that the reference and prediction fits very well with the root mean spread or sequence with the training in the full domain that gives slightly bigger errors. So we talked about that we want to reduce the storage as well. We have focused mostly on the training aspect, getting precise results. And what you see here is actually, if we would have pre-calculated the input responses with traditional method of saving to disk, it would be about 40 megabytes per cube. And you see that for our model, actually the size is bigger. For the L shape, the same. The furthest we get closer, especially if we don't use the modified LNP. And the dome, the reason for this big number here is because of the modified LNP. So the encoder takes in a pretty large domain, so we have many weights in the input data. Execution time, we see that we get well below real time for these cases. For the dome, it's slightly above. And again, we haven't optimized for speed here, but this is again due to this huge input to the branch network. So a bit of outlook: when are these methods useful? So when the acoustic sound field is required to be accurate, these methods seems to be useful. And also, this method is probably most suitable for focusing on the lower frequency sound field, because going up in frequency, this method still gets quite demanding when you go up in frequencies. Also, usual, instead of modeling rooms, it would be interesting to model instruments, because here we need precision. We want the instruments to not to be kind of this instrument, but it needs to be the instrument that you really want to play like. So it could be some old instruments, it could also be some more modern instruments. And we could also choose to model some instruments that doesn't exist, right? So we could build some musical instruments that we have never heard before. So I think this is a very interesting aspect. Okay, now I would like to go to part 2, and this is about our attempt to accelerate the acoustic solo using the numerical methods. So our assumption is that when we have larger rooms, most of the space consists of air. So the idea is to decompose this domain into rectangular domains where we can use some very efficient methods that are not very flexible, and then couple them with flexible methods that can capture the geometry and the boundary material. And this is a method originally introduced by Borrel-Jensen in 2009, where he did exactly that, but he was coupling with the finite time domain method. But as you see here, this method can only approximate geometry with staircases, which might not be accurate enough. So what we want to do is to model it with the spatial method that is more flexible. So our research question is, can we improve the computation time by coupling the Fourier method in rectangular domain with the spatial method near the boundary with acceptable accuracy? So I'd like to just give a broad overview of the method. So let's say that we have a sound field, so it's depicted by this circle here, so this is our sound wave. Now the methods running in different domains, so the Fourier method and the spatial method here, they run in completely separate domains, so they don't have any knowledge about each other. So that means that we have an artificial boundary here that reflects the sound. So we take one time step, the wave hits this artificial boundary and gets reflected back. So now we need an interface coupling that can compensate for this reflection. So basically, what is happening is that we take the reflected pressure, we subtract it, and then we add it to the other side, and we do it in the first line. So this is the overall idea of this method. And I would like to show some results. These are some results in 1D. So what we see here, the dotted line, is where we have our interface between the two methods. So here we have the Fourier method and the spatial method over here. What we first notice is that there is some reflections happening when the wave travels through the interface. What we see here is the impulse response. So this is the, again, think about a microphone here, and then we get the pressure here. And we see that there are some small errors here coming from the reflection of the interface, but they are quite small, so they might be we might not be able to hear them in realistic examples. So these are just some error measures. So if we use a spatial resolution in the Fourier method of 4 points per wavelength and 4 and 12 points per wavelength for the Borrel method, we get between 6 and 9% relative errors. So what we want is to speed up the computation time, right? So this is why we do this. So I have made just a brief absolute timings here. So if you use the Fourier method in half the domain and the spatial in the other half, we get a speed of 2.8 compared to using the spatial method in the full domain. Now, if we increase the area where the Fourier method works, we get around 10 times speed up. And if we use it in 95% of the domain, we get almost 18 times speed up. This table here shows the relative effort used in different methods, so the Fourier method, SEM, and the interface. So when it's like 50-50, the SEM solver takes up most of the computation time. But when we go up see that and it's important to notice the interface is fixed, so it's the same interface. The absolute time of the interface is the same, but when the FM solver takes most of the domain, now the interfaces take up most of the computations. But we see that, yeah, with 95%, the free method takes 10% of the time, and the SM about 20%. Yeah, so because we introduced this interface, this is a non-physical thing we do. So imagine that we have some wave traveling. Suddenly, I introduce some reflection that is reflecting the wave back. This causes some shocks in the system, and it's well known that the SM method has some problem with this, and it influences the accuracy of the simulation. And we also saw some big errors when you couple with high order SM through an interface. So we injected a one-layer SEM with first-order polynomials, and we got the results that we saw before. But this is a problem because when we introduce this first-order layer, the overall convergence of the SEM scheme is determined by this interface, and this ruins the high-order convergence of the SEM scheme. So better methods needs to be researched for this. Okay, to conclude, for the first part, with pins, we showed that we can accurately solve a system of coupled equations for a 1D wave problem with impedance boundaries and parameterized sources. No data was needed, and we got errors between 2%. For the deeper net, we showed that it could accurately and efficiently learn 3D wave propagation in realistic and complex geometries with impedance boundaries and parameterized sources. More geometries were investigated showing good according to the reference model with root mean squared errors between 0.03 per scale and 0.09 per scale. For the accelerated acoustic solver, a 1D Fourier SEM domain decomposition method was implemented, showing notable performance gain with 5 to 10% relative errors. Yeah, a major drawback is the need of first order SEM layer interface. So I would say that my main contribution during my PhD is the fact that our work is the first to accurately model the 3D sound via using machine learning for parameterized source position in realistic and complex 3D scenes executed in real time. And this has been made possible taking a scientific machine learning approach, combining scientific computing and machine learning. Moreover, all the code for all the resources for these projects has been made open source, so it's possible to reproduce everything and also look into the implementation details. So I think this has been my main contributions during these 3 years of work. Thank you very much. Thank you very much.
Thank you, Nicholas, for interesting talk and also the timing. So we will start the question sessions in a few minutes. So let's say 5 minutes to 10 minutes.